Okay, let's continue with chapters E, F, G, or F, G, H, and I in the book. You're just going to keep doing these problems. Let's continue. So we're going to look at unit F, and that's vector between 2 points. So it's very basic. It's like kind of like finding the slope, but instead of the change in y, we're changing x. In vector form, it's at xy, and so simply put, if A is 2, 3, and B is 0.59, the question is, what is vector AB? And it's very straightforward if you think about it. Here's point A, which is 2, 3. Here's point B, which is 5, 9. And so we're looking for AB. So we know that, I mean, you can just visually look at it. So the change in x is 3. The change in y is 6. So AB is the vector 3, 6. Or we learned in the last unit, you could write this as 3i plus 6j. Now, the strict form, now, the question is, the interesting thing is, how do we tie this back to this? How do we connect it to the displacements of vectors and the whole, traveling? So let's think about this. It's kind of interesting. So let's reintroduce the idea of position vectors. Okay. So if point A is 2, 3, then we're going to call OA, starting at the origin and going to point A, as vector 2, 3. And we can call this little a, right? Once again, this is interesting now. Let's move on. Let's take B and turn it into a position vector. So point B is 5, 9. That means that OB, is now vector 5, 9. And that's little b, right? Because we started at 0 and we went 2 to the right, 3 up. 2 to the right, 3 up. We started at 0 and went to B, 5 to the right, 9 up. So the question is, if this is A, and this is B, the question we want to know is, what is this vector here? What is that vector there? Well, if you think about it, it's negative A, right? Because we have to go back here, and then we have to go here. And so that's B plus A, or B minus A, right? So AB. So we would say that AB is actually B minus A, and that makes sense from a distance point of view, because that's how we find the distance. Like, how do we find the distance? Or if we go back, how do we find the slope of like AB, right? We take 9 minus 3 over 5 minus 2. We take the by minus AY over BX minus AX. That's all we're doing. So it's the same idea here. So the final minus the initial, that's kind of like the distance. It all ties together. So AB is vector B minus vector A, and that's the idea. So in the exercise, you're usually going to be asked, here's point A, here's point B, find the vector. Find the vector, A minus AB. Well, what is AB? Well, we know it's 3, 6. What's the magnitude of AB? Well, we quickly know it's 6 squared plus 3 squared. I'm sorry. 3 squared plus 6 squared. What is this? Radical 45. So that's the magnitude. So that's it. That's basically it. Anything else I want to say? No, that's it. That's the whole thing. It seems very basic, but it is. So now we're getting to like 7th grade, 8th grade. So what we're going to do is we're going to expand this. Now we're going to chapter G, which is 3 space. So let's talk about 3 space now. Let's erase this. And try all the problems in haese in chapter F. It's slow and basic, but take it through and then you'll work on it. Let's look at B. Okay, B is fun. I like B because this takes us to the next level. This is 3-dimensional thinking. Okay, so what I want you to do is, let me erase this. What I'd like you to do is, let's see, I want you to draw a square here. Okay, then I want you to draw another square here. Okay, I want you to connect the sides. Okay, so we have a box, okay? What I want you to do is, in green, so this is going to be over here, right here. This is our x-axis, okay? In red, this is going to be our y-axis, and now, actually we can expand this way. Let's expand the x-axis here. And now with the blue marker, or another marker of your choice, let's see if I can find my blue marker. Here we go. Now we have our z-axis. This is our z-axis. Okay, and if we think about this, so let's talk about 3 space. So the question is, let's assume that this is not a perfect cube. Let's assume this is 2 by 3 by 5. Okay, and what we're going to do is, so this is the origin. This is point A, B, C, D, E, F, and G. Okay. Now we're in 3 space. So the question is, how do we identify these points? Well, if you think about it, graph paper, we went along the x-axis to get the x, and along the y-axis to the y. But now we have a third coordinate. So let's think about this. We're going to call the origin 0, 0, 0. How do we get to point A? Well, we go 2 along the x-axis. I'm not going back on the y-axis, and I'm not going up and down. Nice. Point B. How do we get to point B? Well, I go 2 along the x-axis, 3 along the y-axis, and I'm not going up. Same idea with C. What's going on with C? So I don't move along the x-axis. I move back 3 on the y-axis, right? And I don't go up or down. Now let's get to the good stuff. How do I get to point D? Well, how do I get to... You know what? Let's get the good stuff. How about F? How do I get to F? How do you get to point F? Well, I have to go 2 along the x. I have to go back 3. And now I have to go up 5. And this is the third dimension. This is 3-dimensional thing. What about point E? How do I get to E? Well, let's see. I go 2 to the right. I don't go back. I'm on the front face. I'm in the front face. I'm not going back. But I have to go 5 up. What's next? How about D? How do I get to D? Well, I'm not moving to the left or the right. I'm not moving backwards or forwards, but I do have to go 5 up. Last point, G. What do you think? Well, I'm not going left or right. I have to go back 3, and I have to go up 5. And so this is how we represent points in 3 space. And this is points in 3 space. Well, now what we can do is we can represent these all as position vectors in 3 space. So as position vectors, I'll do it in red. So let's think about this. What is OA? Instead of writing 2, 2, 0, now we're going to write 2, 0, 0. How about AOE? Well, this is 2, 0, 5. What's going on with how about F? What's OF? Well, that's 2, 3, 5. Is there another way to write this? Well, we know that we have I and we have J. We're going to use K for the 3rd dimension. So this would be 2I. This would be 2I plus 5K. And this would be 2I plus 3J plus 5K. Now, we can find the position vector. We can turn these points into position vectors. The question is, can I find vectors between any 2 points? For example, oh, I'm sorry, let's just talk about this for a second. So I is now 1, 0, 0. J is now 0, 1, 0. And K is now 0, 0, 1. With these 3 vectors, this is known as the basis. This is known as the basis. Because if you think about it, any combination of integers in front of the I, the J, and the K will get me to any place in my 3 space. Pick any point, and I can get there. 2, 3, 5, 2 times I, 3 times J, 5 plus K will get me to 2, 3, 5. So I can get anywhere in 3 space with these 3, with multiples of these 3 vectors. And the idea in 2 space, the vector is I and J. So with any combination of I and J, I can get to any point. Now the question is, can I get from, for example, how do I find vector A, G? Well, let's see. AG is OG minus OA. So OG, what's OG? OG is, 0, 3, 5. What's OA? 2, 0, 0. Therefore, vector AG is -2, 3, 5. Let's think about this visually, though. It should make sense. How do I get from A to G? Okay, well, I have to go back 2, back 3 along the Y, up 5. 2 to the left, 3 on the Y, 5 up. That makes sense. Pick another one. Anybody, pick anyone. How about I don't know, DF. How about DF? Shall we pick another one? Yeah. How do we go from D to F? What is vector? How about vector? What time? What about vector? How about FD? So FD is OF minus OD. So let's see, what's OF? 2, 3, 5. What's OD? 0, 0, 5. Final answer, 2, 3, 0. So let's see, along the top, FD. FD, let's see, if we don't have the math, how do we literally, we're an ant walking along the box? How do we get there? Well, I have to walk forward 3. I have to walk forward 3. Let's see, let's do the F. I have to go F to G. Oh no, I got this wrong. I'm sorry. Sorry. FD to go from F. Sorry. Okay. So we want F to D. We want to start at F and we want to end up at D. So F is the tip. F is the tail. D is the tip. So it's OD minus OF. Good. So let me get my black pen. Sorry. What is OD? OD was 0, 0, 5. OF was 2, 3, 5. So algebraically, it's -2, -3, 0. Let's think about that mathematically. What's going on? Let's see. I have to go. Good, perfect. So let's think about this mathematically. I have to go 2 to the left. I have to go like the opposite. I have to go like towards, like, I have to go towards the x, change the y, so it's -3, and then I don't change my height. 2, -2, -3, 0. Nice. Let's just talk about some basic things in 3 space. So it turns out that, how are you doing for time? Nice. Okay, let's continue. So let's say we have points, x1, y1, z1, and x2, y2, z2. First of all, the midpoint is x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. This is the midpoint of these 2 points. The question is, and then the last thing is, what's the distance? What's the distance? Well, if you think about it, it's the square root of the change in x's squared plus the change in y's squared plus the change in z's squared. So if you have a 3-dimensional, so this is kind of cool. If, for example, well, let's take a look at this. When we found AG, we found the change in x, change in y, change in z. When we found FD, we found the change in x, change in y, change in z, which means if you have vector AB, which is x, y, and z, the magnitude is now just the square root of x squared, y squared, z squared. So this makes vectors really interesting. Once again, all the components in the vectors are the changes. So you can easily find the distance. Now this is kind of cool because now we have a fast way for finding the diagonal of a cube. So find the diagonal, find the length of the diagonal of the cube, this cube, right? And you say, oh, you know what? Well, the diagonal has a vector of 2, 3, 5, because the diagonal is OF, right? So therefore, it's the square root of 2 squared plus 3 squared plus 5 squared. Final answer, the square root of 13 plus 25, 39. No, 38, sorry. And this is the idea. So now we're moving into 3 space. Follow along the exercises in the book. It's very straightforward. Magnitude 3 space, all operations are the same. So once again, so everything in 3 space is just an extension of 2 space. So for example, let's say I have a vector AB is, 5, 1, 6, and let's call that A. Let's call that, I don't know, let's call it C. So 2C is simply 2 times 5, 1, 6, which is simply 10 to 12. What is negative 3C? Well, it's negative 15, negative 3, negative 18. It's simply 3. It's simply C, 1, 2, 3, but now in the opposite direction. That's basically, it's all the same stuff. So 3-dimensional thinking is just an extension of 2-dimensional thinking. The vectors work out. And there's just tiny little exercises in haese that, prove that, so here's another thing you might be asked to prove. For example, prove that prove that the magnitude of Ka is equal to the magnitude of K times the magnitude of A. Just a little proof. So for example, let A be x, y, z. So we know that A is the square root of x squared plus y squared plus z squared. So we know that Ka is equal to kx, ky, kz, which is equal to the square root of k squared x squared plus k squared y squared plus k squared z squared. Factor out the k squared, factor out x squared plus y squared plus z squared, and we have the magnitude of k times the magnitude k times the magnitude of a. And so that's the idea. These are little haese exercises. Go through all of them. What else do you want to talk about? And last thing is something called parallel. When are two vectors? So now we have two vectors in 2 space, but we also have vectors in 3 space. And the first thing we want to talk about is the relationship between those 2 vectors. So let's move on to the last little unit, which is little unit I, and that's called parallelism. And the question is, 2 vectors, A and B, are parallel if A is equal to KB for any scalar K. And that's the idea, is that, so for example, is 2, 5 parallel to 4, 10? And you would say yes, because 4, 10 is equal to 2 times 2, 5. That's it. Now, knowing that vectors are parallel, you could also figure out if they're collinear. So if you can use this knowledge to determine if 3 points are collinear. So you have 3 points. Once again, now we're not only in 2 space, but we could also think about this in 3 space. So for example, I might say this point, well, I'm going to take this off. Any examples? How about this is 1, 2, 3. This point B is, I don't know, let's see, 5, 10, 2, 4, 6, and point C is 10, 10, 20, 30. So the question is, are these points collinear? Are they on the same line? And if you recall from your geometry, maybe not, what you would do is you would first find vector AB, and then you would find vector BC. So this is how you figure out, so now we have all these points in 3 space. You can actually plot this in GeoGebra, and you can actually take a look. So let's see, first thing we want to figure out is BA. Well, BA is, let's see, we have 1, 2, 3. And now we've figured vector B, I'm sorry, this is AB. Right, and now we want to figure out vector BC. What's vector BC? Let's see, that's 8, 16, 24. And the question is AB equal to KBC? Well, we can do the other way. So can we make a claim? And you might recognize, oh, you know what, Mr. Adler? BC is equal to 8 AB. So because these are parallel to each other and B ends, so because they are parallel and because B is the tip of AB and the tail of BC, A, B, and C are collinear. Okay, so we're done with the basic stuff of like the basic arithmetic and algebra. So I want you to do over the next week is I want you to go through every single problem in HES, 14A through 14I. We'll talk about, we'll spend a day next week going through every single problem. When we're finished with that, then we can start the dot product and the cross product, and then we're really taking it up to, higher level math. Once you finish chapter 15, then we can go into once we finish chapter 14, then we can take it up to the next level, chapter 15. That's going to be a delight. That's where we're going to conclude the year with that. Good.